Here is your second video on your Chapter 12 notes on Unit 4. In this video, we're going to hopefully be able to get to your Practice B problems, but I would like to finish a few slides on your Practice A information. For instance, we left off with the two factors that determine which sounds are audible, are intensity and frequency. So with that in mind, what we're also looking at is the threshold of hearing, in which the threshold of hearing is the softest sounds heard by the average human ear. Softest sounds heard by the average human ear. Okay? This range is going to be at 1,000 hertz, but it's also going to be measured in intensity, and that intense value is 1.0 times 10 to the negative 12 watts per meter squared. The opposite of this is called the threshold of pain. This is the loudest tolerable sounds heard by the average human ear. The loudest tolerable sounds heard by the average human ear. Okay, that range is going to be above 15,000 hertz, which is going to give it an absolute sound intensity of 1.0 watts per meter squared. So you can see that we're going to get into, we could, at least with decibels, some logarithms on these values, log base 10, etc. First, second, third decibels. Here's the chart that I'm referring to. Relative intensity, not absolute sound intensity, but relative intensity is measured in decibels. Please do not be lazy on this. It is a lower D, big B. It is also known as the decibel level. Here's the thing you need to concentrate on. When intensity is multiplied by 10, then 10 decibels are added to the decibel level. This picture was taken from Table 2 on page 417 in your Holt book. Please look at the relative decibels of some of these different values. You'll need to refer back to this, so please make sure that you are aware that Table 2 on page 417 is something that you'll need to look at again. Okay, forced vibrations. Which pendulum begins to move as you set the blue one into motion? Well, the first thing I want you to look at is period. It's 2 pi square root, period of a simple pendulum. You just took the quiz on it. Period of a simple pendulum. What are the two factors that are going to influence the period of a simple pendulum? That is going to be the length and free fall acceleration, or in other words, acceleration due to gravity. So, what is the thing you guys are going to look at here? Well, I didn't tell you you went somewhere different, like the moon, Mars, etc., etc. So you can safely assume that your G is a constant. Obviously, 2 pi is a constant. So length is going to be what affects the period. And what I want to look for is when you set this blue pendulum bob into motion, which other pendulum, 1, 2, or 3, is going to oscillate with the same set of vibrations. In other words, the same period. So it would be the one with the same length. Agreed? So therefore, number 2 is going to oscillate with the same motion, forced vibration. Why? Equal lengths. Equal lengths. Okay, vibration at a natural frequency. Vibration at a natural frequency. What we're looking at here is the idea of resonance. It's a pretty powerful word when we're talking about sound. And resonance is defined as applied frequency, so you're going to apply a frequency to a system, matches the natural frequency of vibration for a system. Every system has a natural vibration to it. For instance, when you build stadiums or when you build bridges When you build skyscrapers, you've got to be able to calculate what the natural frequency is, especially for the air, in other words, the wind, that's going to be moving through the system, because if the forced system matches the natural frequency, then you're going to have some major destruction, hence the Tacoma Narrows Bridge incident. Very great video here. You do have questions, or will at least have questions that deal with this on some upcoming assessments. Please watch that video. Okay, for resonance, applied frequency matches the natural frequency of vibration for a system. Like the Tacoma Narrows Bridge incident. Please watch that video. Okay, harmonics. Fundamental frequency. The fundamental frequency is the lowest frequency of the vibrating object. One thing that you're going to have to keep in mind is that n equals 1. Okay, please make sure you jot that down, guys, because like on your challenge problems and stuff, I'm going to say at a natural frequency of 60 hertz or whatever. Well, you'll see in the equation that you're going to use that you still need an n value, the number of harmonics, so that n is going to be 1. So what are harmonics here? Harmonics are integral multiples of the fundamental frequency. In other words, when n equals 1 is going to be the fundamental frequency. Are you going to be talking about 1, 2, 3, 4, 5 harmonics, or 1, 3, 5, 7, 9? In other words, odd harmonics. It will be based on the idea of an open or a closed tube, instrument, whatever, that is generating that sound. So we have the harmonic series. This should be real. I'm just going to run through it real quick. So your nodes are going to be where there are fixed ends, in other words, no vibration. Your antinodes are going to be halfway between two nodes, is where you're going to see an antinode. Hence, this is going to be the first harmonic, second, third, fourth, and fifth, respectively. Does the string vibrate at any of the node positions? No, because there is no displacement. More explicitly, you are at what position, guys? You're at what position if you have no displacement? Equilibrium. Okay, what area of the sine wave are you measuring when you're at an antinode? Well, if you had no motion, this is your equilibrium line, agreed? So what value is it that you're going to be measuring to see what your antinodes are? What's that other A word? Amplitude. Height of a wave from equilibrium position. Height of a wave from equilibrium position. So determining the harmonics. What do you count to determine which harmonics you're observing? You count the antinodes. But once again, remember, in order to be an antinode, you have to be between two nodes. So is this a node? Yes. Is this a node? Yes. So here is the first harmonic. This would be the first, second, third, fourth harmonic. So in other words, n equals 1, n equals 4, whenever you're going to do your problems here. The equation that you're going to use is f of n equals nv over 2L, whereas f of n is your frequency. It might be the fundamental frequency. It is going to be measured in hertz. Your n is your number of harmonics. They do not count for sig figs, so I'm going to put sig fig equals no. Okay, they're not going to count for sig figs. Your v is going to be your velocity, at which speed are those sound waves traveling at, obviously meters per second. And L is your length of the string, the tube, the whatever. And that's going to be measured in meters. Once again, N is a whole number, no decimals, regardless of how many sig figs you're talking about. So if I would ask you to solve for N, your final answer is just going to be a whole number. Pipes that are open at both ends, are all harmonics present? Yes. So you'll be able to calculate 1, 2, 3, 4, 5, 6, etc., etc. What is present at both ends? That is going to be an antinode. Okay. Another equation, when the pipes are open at both ends, it's not really another equation, it's the same exact one. F of n equals NV over 2L. So that's an open pipe, an open instrument. I'm not going to take the time to write those out. You've already done that before. So why does this resemble a harmonic series? Because all harmonics are present. You can solve for N1, N2, N3, N4, etc. So pipes that are closed at one end, no, they are not, because you have an antinode at one end and a node on the opposite end. One end is a node, no displacement, the other end is an antinode. So therefore it is a closed pipe. So if I would give you a problem that says an antinode and a node, then you know you're going to use this equation right here. F of n equals NV over 4L. Everything still stays the same, guys. Your F of n is hertz, your n is your harmonics, your velocity is your v, your length is still in meters. It's just the difference is 4 is going to be for closed, whereas 2 is for open. A sax, for instance. Actually reed instruments, woodwinds, not flutes, so obviously they don't have a reed on them, would be an example of that. So this is called an Alp horn. You know, you have one of those questions on your challenge problems. Okay, so the first three harmonics in length is 2.45 meters. That is opened at both ends. So the first ones you want to solve for when n equals 1, and then when n equals 2, and then when n equals 3. And the speed is going to be 345 meters per second. You want to solve for Fn, that's the natural frequency, is 1. In hertz, you want to solve for F2, and you want to solve for F3 in hertz. You want to do this for open, and then you want to come back and do this for closed. So your open equation is Fn equals NV over 2L. You want to try to solve for F of n. So 1 times 345 divided by 2 times 2.45. Putting that into a calculator, 345 divided by 2 times 2.45 is going to give you 70.4, in which you want 3 sig figs. So your F of n is 70.4 hertz. Guys, if everything is present, 1, 2, 3, 4, 5, etc., etc., real quickly, how can you figure out the second one, the third one, etc.? All you have to do for F2 is say 2 times 70.4. You can do that in your head. 140.8. Wow, 40.8. So your F2 is going to be 141 hertz. Therefore, what is F3 going to be? Well, F3 is going to be 3 times your natural frequency. That one you could do in your head as well. Long story short, F3 equals 211 hertz. Okay? So now we can go through and do the closed as well. Your closed is going to be F of n equals NV over 4L, in which you have 1 times 345 divided by 4 times 2.45. Figure that guy out, and then you're going to do 3 times your natural frequency. And then you're going to, that's your second harmonic, right? And then you're going to do F equals 5, so 5 times your F of n, because these are the odd harmonics. The odds are what are present for a closed pipe. Here's your next page, which are your answers to your practice B problems. These are your answers to your practice B problems. You have 2 more sample problems that I'm giving to you, like, let's try one more. Okay, try one on your own. Those 2 answers are both, ironically enough, 440 meters per second. Please make sure you try those two. I'm going to now make a video on your last couple of slides here on beats. You do have a challenge problem that is explicitly about beats. Try practice B now, please.